Welcome to all of you. Now we discuss about the question paper 2022 semester 5 CBCS B.Sc Honors in Mathematics paper D.Sc B1.2 MTMA LPP and Game Theory question paper University of Calcutta 2022. This is the question paper 2022 LPP and Game Theory, Linear Programming and Game Theory. Is question 1A. For the following LPP, the optimal value of the objective function will be what? Here we solve this subject to the function this, and this 3x1 plus x2 less than equal to 3, x1 greater than equal to 0, x2 greater than equal to 0. So we get this line and x1 equal to 0 this line and x2 equal to 0 this line, and this is the feasible region, and the z0 at origin value is 0 and z at the point a 0 3 value is 9 and zb the value of this function z is 2. So maximum z equal to 9 for the point a. So we use the theorem, the objective function this z of a LPP attains its optimal value if it exists at an extreme point of the convex set of feasible solution. Correct option is 2. Next 1B, which one of the following is a convex set with infinite number of extreme points? Correct answer is 3. This let x1 dash x2 dash x1 double dash x2 double dash belongs to the set capital X, where capital X is this, the set of all those order pair x1 x2 belongs to the Euclidean place, two-dimensional Euclidean place E2, such that x1 square plus x2 square less than equal to 16. So this is a circle center at origin and radius is 4 unit. And then this is the interior point and the boundary point of this circle. This is the set X, convex set X. Now obviously any point x1 dash x2 dash x2 x1 double dash x2 double dash on the set this, then x1 dash square plus x2 dash square less than equal to 16, x1 double dash square plus x2 double dash square less than equal to 16, and convex combination this lambda into this point plus 1 minus lambda into another point, and that is this first component addition of first component addition of second component, where 0 less than equal to lambda less than equal to 1, and we get this addition of this first component plus first component square plus second component square, this for this point we get this, and we use here this x1 dash x2 dash square is less than equal to 16, x1 double dash square plus x2 double dash square less than equal to 16, and after simplification we get this result is equal to 16, and so lambda x1 dash plus x1 dash comma x2 dash plus 1 minus lambda x1 double dash comma x2 double dash belongs to the capital convex set X for 0 less than equal to lambda less than equal to 1. Hence capital X is a convex set, obviously. Answer correct option is 3. Question C. The intersection of two convex sets may or may not have a convex set, is not a convex set, is a convex set, none of 1, 2, 3 and correct option is 3. Intersection of two convex sets is a convex set. And proof here we let capital H is the set of all those X alpha convex set of all convex set, where alpha belongs to the natural number n. The family of convex set where capital N is a set of natural numbers, and let capital X be this equal to the intersection of X alpha, where alpha belongs to n. We are to show that capital X is a convex set. If capital X is equal to 5 or capital X is a singleton set, then trivially capital X is a convex set. And let x comma y belongs to capital X, then x comma y belongs to X alpha for all alpha belongs to n. As each X alpha comma alpha belongs to n is a convex set, so lambda x plus bracket 1 minus lambda y belongs to X alpha 0 less than equal to lambda less than equal to 1 for all alpha belongs to the natural number set n. Therefore, lambda x plus 1 minus lambda into y belongs to the intersection of X alpha belongs to n, that is equal to x. Hence, capital X is a convex set. Therefore, the intersection of two convex set is a convex set. Hence, the correct option is 3. Question D, the following LPP, this maximize z equal to this, subject to this, has 1 feasible, 2 feasible solution, infinite number of feasible solutions, no feasible solutions. Here, the subject to this constraint, this we draw the graph for these constants x1 plus x2 equal to 1, minus 3x1 plus x2 equal to 3, and so we get x1, this equation, first equation is this x1 plus x2 equal to 1, and minus 3x1 plus x2 equal to 3, and this is the line, and according to inequality, so we get this region, this and this region, and as there is no point x1 x2 common to the both shaded region, so the given LPP that has no feasible solution, correct option is 4. Question E, the minimum cost for the transportation this O1 O2 origin and destination D1 D2 1 2 3 2 cost price, and this the 5, and this the total demand is this D1 O1 is this source, this demand is this D1, so we minimum cost price for this transportation. Question E. By Vogel approximation method VAM, we get initial basic feasible solution is this x11 equal to 5, x21 equal to 7, and x21 equal to 3, and x22 equal to 7. And so cost is this 5 into 1, 3 into 3, 7 into 2, so 28. And delta ij, cell evaluation equal to Cij minus bracket ui plus Vj. Here this ai equal to 5, 10, and Bj equal to 8, 7. So ui equal to this maximum allocation along this row. So put here ui equal to 0, and then so we write here 3 and 2 for that 0 Vj, value of Vj, and this ui for this allocation 3 minus 2 equal to 1, and so this is minus 2, and here Ci minus bracket ui plus Vj for unoccupied cell, that is here only one unoccupied cell, 2 cell, so delta 1 2 equal to 2, this in circle, encircle this 2, this positive, so above solution is optimal, and the minimum cost is 28, so answer is 28, option 3. Question A, if the primal problem has n constraint with n variables, then the dual problem has, correct option is 2, n constraint with n variables, as the number of variables in the dual is equal to the number of constraint in the primal and vice versa, so the correct option is 2. Here primal problem n constraint and n variables, so in the dual problem n constraint and n variables, so correct option is 2. Question G, in 2 by 2 pair of matrix 6, 1, x 5, the value of the game is 5, then the value of x is what? Here, this is the pair of matrix, player A and player B. There are option 1 and option 2, player B for player B. There are two options 1 and 2. This value of this 1, 6, 1 and x5, we ignore x and compute the row minimum and column maximum. So row minimum is this 6, 1, 1, minimum is 1, x and 5 is ignore x, so row minimum 5. Column maximum is 6 and 5. And new lower bar is the maximum for A. That is the maximum of the row minimum. So maximum row minimum is 1, 5, so maximum is 5. So new lower bar equal to 5, and new upper bar is the minimax for B, that is the minimum of column maximum. So column maximum is 6, 5, so minimum value is 5. So new upper bar is this, hence new lower bar equal to 5, new upper bar equal to 5, hence the value of the game new equal to 5. Clearly, obviously x equal to 5, as new equal to 5, then x greater than equal to 5. So correct option is value of x is 5. Here value of the game is 5 is given, value of the game is 5 is given. So obviously greater than equal to 5, value of this. Correct option is 4. Question H, in a simplex method, if the optimality condition is satisfied at any iteration and the basis contains one or more artificial vectors, the corresponding artificial variable at 0 level, then the solution obtained what? Question H. If one or more artificial vector present in the basis and the corresponding artificial variables appears at 0 level, then the solution is optimal, and hence the constant equations are consistent, though one or more constant may be redundant. So correct option is 1. Question I, suppose in a traveling salesman problem, the salesman has to visit n cities, then the number of possible routes are option 4, factorial minus 1. A salesman must visit n cities, passing through each city only once, beginning from one city called a base or starting city, and returns to it. Then there are n minus 1 factorial possible route to visit all cities. And for example, this is A, B, C, D. So possible routes are 4 cities. So possible routes are these here: 1, 2, 3, 4, 5, 6, or possible routes. Here B in 3 ways, C 2 ways, D is 1 way. So 3 into 2 into 1, that is the 6, that is equal to factorial 3 in minus 1 factorial. Correct option is 4. Question J, for the system of equations, the solution x1 equal to 5, x2 equal to minus 1, x3 equal to 0, basic and feasible, feasible but not basic, degenerate basic, non-degenerate basic. Here, the given system can be rewritten as Ax equal to B, where A is the coefficient matrix 1, 2, 1, 2, 1, 5, and capital X, x1, x2, x3, and B is the value cost matrix, this 2, 5, right hand side value of the matrix this. Now x1 equal to 5, x2 equal to minus 1, and x3 equal to 0 are given here, the solution of the system, as this x3 is 0. So corresponding vector, column vector 1, 2, 2, 1, consider this determinant for this non-zero values x1, x2, determine this not equal to 0, minus 3. The associated column vectors a1, 1, 2, and 2, 1, this of the matrix A corresponding to non-zero values x1 equal to 5, x2 equal to minus 1 are linearly independent, because this determinant not equal to 0. So the solution capital X 5 minus 1, 0 is a basic solution of the system. Since x2 is minus 1 less than 0, so the solution is is not a feasible solution. And since x1 equal to 5, x2 equal to -1, so non-basic variables vanish, no non-basic variable vanishes. Then the basic solution is called non-degenerate basic solution, but non-feasible solution. And x3 equal to 0, non-basic variable. So correct option is non-degenerate basic, option 4. Next, unit 1, question 2, answer in 2 questions. 3 different types of lorries and this formulate this problem in LPP and form to find the minimum transport cost. We construct this table. This is the A, B, and C lorries, and this solid, liquid, and transport cost solid in tons. A lorry is 7 ton cost. This ABC 6 ton solids, 35 tons liquid. This lorries ABC used to transport this total this 60 tons solid and 35 ton liquids. An A-type lorry can carry 7 ton solid. A-type lorry 7 ton solid and 3 ton liquid. A-type lorry. And B-type lorry 6 ton solid and 2 ton liquid. And C-type lorry can carry 3 tons solid and 4 tons liquid. The cost of the transport are rupees 500, 400, and 450 per lorry ABC type respectively. Formulate this problem LPP to form the find minimum cost. X1, X2 is the number of lorries. We suppose here X1 is the A-type lorry, X2 is the B-type lorry, and X3 number of lorries, C-type lorries. So Z is equal to 500 X1 plus 400 X2 plus 450 X3. The objective function is the value of this A-type lorry is 500, 400, and 450. The quantity of solid transported by the lorries is 7x1 plus 6x2 plus 3x3 tons. This solid, so this solid is 60 tons. So this greater than equal to 60. Similarly, for the liquid substance, this is greater than equal to 35. So we get the objective function minimize z this and subject to this constant this and the non-negativity restriction x1, x2, and x3 greater than equal to 0. x1, x2, and x3 greater than equal to 0. And x3 greater than equal to 0. x3 greater than equal to 0. Next question. x1 equal to 1, x2 equal to 1, x3 equal to 1, x4 equal to 0 is a feasible solution of the system of equation. This reduce the solution to two different basic feasible solutions. So capital A is the coefficient matrix, capital X is the column matrix x1, x2, x3, x4, and B is 7, 4 is the column matrix. Clearly, rank of A is 2. So there are at most 2 linearly independent column vectors of A. So A1, A2, A3, A4 are linearly dependent. Thus, x1 equal to 1, x2 equal to 1, x3 equal to 1, x4 equal to 0 is not a basic solution, as the basic solution will contain not more than 2 non-zero variables, because this the rank is 2 here. At the column vectors, this A1 is 1, 2, A2 is 2, 1, A3 is 4, 3, and A4 is 1, minus 2. We write the given equation as x1a1 plus x2a2 plus x3a3 plus x4a4 equal to b. For the given feasible solution 1, 1, 1, 0, it is given that this we have this for this put this x1, x2, and x3, x4, a1 plus a2 plus a3 equal to b. The given solution being not basic, the vectors a1, a2, a3 are linearly dependent, and we assume this lambda 1 a1 plus lambda 2 a2 plus lambda 3 a3 equal to the 0 vector. This 0 vector is 0, 0 column vector, where at least one of this lambda 1, lambda 2, lambda 3 is not 0, and here lambda 4 is 0. So lambda 1, 1, 2, plus lambda 2 2 1 column vector lambda 3 4 3 and this 0 0, and we get two equations, lambda 1 plus 2 lambda 2 plus 4 lambda 3 equal to 0, and 2 lambda 1, sorry, this is lambda 1, this lambda 1 2 minus lambda 2 plus 3 lambda 3 equal to 0. And after simplification we get cross multiplication, lambda 1 by 2 equal to lambda 2 by 1 equal to lambda 3 by minus 1 equal to k. Assume k equal to 1, then lambda 1 equal to 2, lambda 2 equal to 1, lambda 3 equal to minus 1. The dependence of a1, a2, a3 is then 2a1 plus a2 minus a3 equal to 0 vector. And for lambda j greater than equal to 0, lambda 1 greater than 0, lambda 2 greater than 0, the criteria determining the vectors which are to be eliminated is given by xr by lambda equal to minimum value of j, xj by lambda j, where lambda j greater than 0 is equal to minimum over j, and x1 by lambda 1 comma x2 by lambda 2. So minimum is this 1 by 2 comma 1 by 1, that is 1 by 2, this equal to x1 by lambda 1. Hence the new solution is obtained: x1 minus x1 by lambda 1 to lambda 1, x2 minus x1 by lambda 1 lambda 2, comma x3 minus x1 by lambda 1 to lambda 3, x4 minus x1 by lambda 1 to lambda 4 whole transpose, it's column vector. So we get 0 comma half comma 3 by 2 comma 0 in this column vector. Answer: this is the basic feasible solution, as these a1 and a3 are the linearly independent, because this corresponding a1 vector a3 vector determinant is minus 5 not equal to 0. For lambda j negative, that is lambda 3 is negative, this lambda 3 negative, this minus 1, so lambda 3. The other criteria for the lambda j negative, the xr by lambda are equal to maximum xg by lambda j negative, maximum of xg by lambda 3, that is maximum of x3 by lambda 3 is minus 1, is minus 1. Then the new solution is then given by this, we get 3 2 0 0 transpose column matrix, and this is another basic feasible solution, and this corresponding this 3 and 2, first a1 and a2, this not equal to 0, and associated column vector corresponding to this, the new non-zero variables are linearly independent, so this is a basic solution of the given system. Next question. Question C, define convex polyhedron and convex hull. Give an example of each of them. Check whether the set is convex or not. The set of all convex combinations of a finite number of points is said to be a convex polyhedron or polytope, with these points as vertices of the polyhedron. Let capital X is a subset of En, equivalent space, n-dimensional equivalent space En, the set of all convex combination of points of X, denoted by Cx, is called convex hull of X. Example: convex hull of a set containing three non-collinear points of En is the triangular region having the 3 points as the vertices, and this is also a convex polyhedron. This example is this. And convex hull of a set of points lying on a boundary of a circle is the circular disk. It is not a convex polyhedron because it has an infinite number of extreme points. This is the convex hull. And the question second part, this set capital S is the set of all these is convex or not. For checking this, first inequation, convert this first equation, and then determine this inequality. This first equation, this second equation, this third equation, this x1 2x1 plus 3y equal to 6. This equation, we get this inequality region. This, so we actually this is the line segment is this. This is the line segment actually from this is convex. This set, check whether this set this less than equal to this less than equal to this equal to. So this set contains only the points on this set. So this set is convex set. Only the points on this line segment are this. Question 2D. State the fundamental theorem of LPP. Prove that the set of all feasible solutions to an LPP Ax equal to B, capital X greater than equal to 0 is a closed convex set. So this fundamental theorem of LPP If the LPP admits an optimal solution, then the optimal solution will coincide with at least one basic feasible solution of the problem. The set of all feasible solutions of a LPP is a convex set. Consider the constant Ax equal to b, x greater than equal to 0 vector. Let S be a set of feasible solutions of this problem, and if capital X1, capital X2 be two feasible solutions belongs to the capital S set, then Ax1 equal to b, Ax2 equal to b, and capital X1 greater than equal to 0, capital X2 greater than equal to null vector, this zero matrix. Let X3 be the convex combination of X1 and X2, then X3 equal to lambda X1 plus 1 minus lambda X2, 0 less than equal to lambda less than equal to 1. Then Ax3 equal to this, so we get lambda b 1 minus lambda into b, this equal to b. So X3 satisfies constraint equation of the given LPP. Now X1 greater than equal to 0, X2 greater than equal to 0, and this lambda 0 less than equal to lambda less than equal to 1, and therefore lambda X1 greater than equal to 0, 1 minus lambda X2 greater than equal to 0. Since lambda and 1 minus lambda are both non-negative, then X3 obviously greater than equal to 0, thus X3 is a feasible solution and X3 belongs to S, thus S is a convex set. And this convex set is bounded from below as X is greater than equal to 0 vector. Again, all the points of the hyperplane Ax equal to b form a closed set, and the set of all points X for which X greater than equal to 0 vector is also closed. Thus, the convex set S being the intersection of these two closed sets is also closed, hence the result. Unit 2, question 3. Apply simplex method to solve the following problem. Maximize z equal to this, subject to this. So we introduce here slack variables x3, x4, and we rewrite these inequalities to equal equation, and we construct these simplex tables. This table 1, initial table, and table 2 and table 3, and this is the details calculation, and last table in this final table, the all zj minus cj greater than equal to 0, the solution is optimal, and x1 equal to 20 by 9 and x2 equal to 45 by 9, and the minimum value of z is this 235 by 19. 20 by 19, 45 by 19, and this 5 into x1 plus 3 into x2. Question 3a2. Solve the following LPP by penalty method. Maximize this, subject to this. Introducing two artificial variables x4 and x5, the given LPP can be written as this m1 and m2. This m is the sufficiently large positive number here, and this is the simplex table, this first table and second table. And for this, since all zj minus cj greater than equal to 0, but the artificial vector present in the basis, the corresponding a4 artificial vector a4 is present in the basis, and the corresponding artificial variable x4 is present in the positive level, so the LPP has no feasible solution on this problem. Question 3bi. Use two-phase method to solve the following LPP. Minimize z equal to this, subject to this. Here two-phase method, here maximize z1 equal to minus of minimize z equal to minus x1 minus x2 minus x3, introducing slack variable x4, surplus variables x5, and two artificial variables x6 and x7. We write the LPP in standard form as this. Phase 1, the auxiliary objective function is to be maximized z star equal to this 0 into x5 minus x6 minus x7, and subject to the above constraint, we this get the initial phase 1 in the final table in the phase 1, since zj minus cj greater than equal to 0, so the condition of the optimality is satisfied, and also no artificial vector present in the basis, so the optimum BFS, basic field solution of the auxiliary LPP, has been attained. And phase 2 for this objective function is this z1 equal to minus x1 minus x2 minus x3, 0x4 0x5, and which to be maximized. And for phase 2 we construct this table. Since all zj minus cj greater than equal to 0, the solution obtained is optimal, and the optimal solution is x1 equal to 0, x2 equal to 1, x3 equal to 2, and minimize z equal to 3. Question 3b2. So the simplex method. So by simplex method, that the following problem has an unbounded optimal solution. Maximize this subject to this. Here, the introducing slack variables x3 greater than equal to 0, x4 greater than equal to 0. We rewrite this problem, maximize z equal to this, subject to this, and we construct this simplex table, table 1, table 2, table 3. Here, z3 minus c3 equal to minus 4. This is negative, and all and yi3 negative. This minus 1, this minus 2 along this column. So the given problem has unbounded solution. Unit 3, question 4A1. If X be feasible any feasible solution to primal problem and V be any feasible solution to its dual problem, then prove that Cx less than equal to B dash V, where C and B are respectively the cost vector and requirement vector of the primal problem. Here consider the LPP primal in the matrix form. Maximize Z is equal to C transpose X, subject to this Ax less than equal to B, and this capital X greater than equal to column matrix 0 vectors 0 0 0 n by 1, and the corresponding dual problem is this B transpose V, subject to this Aij j equal to 1 to m Vj greater than equal to Ci I from 1 to n, and Vj greater than equal to 0 for j equal to 1 to m. That is A transpose V greater than equal to capital C and V greater than equal to 0 vector. Here C transpose is the column vector C1, C2, Cn. Capital X is the is the row vector. Sorry, C transpose is row vector within the first bracket parenthesis, and capital X is the third bracket is the column vector, and B is the column vector B1, B2, Bm. B is n by 1 vector, m by 1 vector, and capital A is the coefficient matrix, this Aij m by n matrix, and capital V is the column vector m by 1 size V1, V2, Vm. A transpose is the transpose of the A matrix Aij n by m, and this B transpose B1, B2, Bm 1 by m, and this, and C is the C1, C2, Cn n by 1 column vector. Primal problem, maximize Z is the C transpose X, subject to Ax less than equal to B, capital X greater than equal to null vector, and dual problem, minimize W, B transpose V, subject to A transpose V greater than equal to C vector, V greater than equal to 0 vector. Multiplying Ax less than equal to B by V transpose from the left side, we get this, and after simplification we get V transpose this 1 by 1 and this. So this is the equation 1, inequality 1, and again pre-multiplying by X transpose on A transpose V greater than equal to C vector, we get this, and this A transpose B transpose A transpose, the matrix definition from matrix transpose of matrix. So this is the AB whole transpose equals to B transpose A transpose. So from this we can write this. So V transpose AX greater than equal to C transpose X in equation 2. Combining 1 and 2, we get C transpose X less than equal to V transpose AX less than equal to B transpose V whole transpose equal to, that is B transpose V. That is C transpose AX less than equal to B transpose V. That is Z is less than equal to W. This is the called the weak duality theorem. And according to this Mukta Chakraborty course, we can use C in place of C transpose throughout the proof. Next question, 4A2. Formulate the dual of the following LPP. Here, this x3 is unrestricted in sign, and set x3 equal to x3 dash minus x3 double dash, x3 dash and x3 double dash greater than equal to 0. The given LPP can be rewritten as maximize z equal to this and subject to is this, and considering u dash and u1 double dash, u2 and u3 as a dual variables, the dual of the above primal, we can write minimize w equal to 7 u1 dash minus 7 u1 double dash plus 3 u2 minus 5 u3, and subject to this, we get u1 dash u1 double dash u2 u3 greater than equal to 0, putting u1 equal to u1 dash minus u1 double dash. This is a dual and can be written as this minimized w equal to 7 u1 plus 3 u2 minus 5 u3, and subject to u1 plus 2 u2 greater than equal to 2 minus 5 u1 minus 5 u2 minus 3 u3 greater than equal to 3, 3 u1 plus u3 greater equal to 4, and u2 u3 greater than equal to 0, and u1 is unrestricted in sign. Question 4b, use duality to find the optimal solution of the following problem. And the optimal solution of the following problem, this following problem. Consider u1, u2, u3 as the dual variable. The dual of the given problem can be written as maximize w equal to this subject to this. Introducing slack variables u4, u5, u6 for this first and second and third in equations respectively, we get this maximize w equal to this subject to is this, and we construct this table for this, and this is the final table. And since all z minus cj greater than equal to 0, so the optimality condition is satisfied, we get the optimal solution. u1 is equal to 1, u2 equal to 0, u3 equal to 3, and the maximum w equal to 10. The optimal solution of the primal problem is obtained from the net evaluation of the corresponding slack variables u4 and u5 and u6. u4, u5 and u6 here. u5 is this x1 equal to 6 and x2 equal to 2 and x3 equal to 0, and minimize z equal to 10 also. Next, unit 4, question 5a. Solve the following transportation problem this. So this is the balance TP, because this summation of ai and summation of bj equal. We find initial basic feasible solution by Vogel's approximation method. The difference between the lowest and the next to lowest cost written within the first brackets, and against each row and column. The maximum of these differences is 7, which corresponds to the third column. We look for the minimum cost is the third column, and so on. So applying Vogel's approximation method, initial basic feasible solutions x1 3 is 15, this x22 equal to 15, x24 equal to 10, and x31 equal to 5, and the minimum m plus n minus 1 is this 6, this is greater than equal to 4. The number of basic variables, this m plus n, and this equal to 4. So 4 is the number of basic variables, so m plus n plus minus 1 is greater than equal to the number of basic variables. So initial basic variable solution is degenerate. To resolve the degeneracy, we require two more cells. We select 2, 3 and 3, 3 and allocate negligible small positive quantity epsilon greater than equal to 0 to these cells. So select this 2, 3 and 3, 3. This 2, 3 and 3, 3. 2, 3 and 3, 3 is cell. And do not form a loop with the other occupied cell. So we do not form a loop with the other occupied cell. And this cell and this cell, we cannot form a loop on this. And we find this cell evaluation, this 6, 18, 18, and this 7 and 1 and 6, ui and vj. Calculate this number of allocated cells is maximum in the third column, and we calculate u1, u3, u3, so that Cij is equal to ui plus vj for the allocated cells. And now we determine the cell evaluation delta ij equal to Cij minus bracket ui minus plus vj of the unoccupied cell, and exhibit then in a circle in the upper and left corner of the respective cell. Encircle this column cell evaluated value. And the optimal solution is this x13 is 15, here x13 is 15, x22 is 15, x31 is 5, and this 0 and 0. x24 is 10, x24 is 10, here this, and x33 is 0, epsilon is 0, and x23 is 0, this epsilon is tends to 0. So minimum cost is the 365 units. Question 5b. Solve the following TSP so as to minimize the cost per cycle. This using the Hungarian method, we first solve this problem as an optimal assignment problem. This row operated cost matrix and by column operation, and the number of straight lines to cover all zeros in table 2 in a reduced matrix is 4. This line, this line to cover the all zeros, this line. But here we get 4 lines, but not equal to the or 5, that is the order of the cost matrix. So we construct a new table again. So here we construct this table 3, and this here the 4 lines cover up the all zeros. So it is not also the we construct the new table, and this table 4 and table 5. In table 4, this 1 assign these 2, 1 to 2, and this 2 to 4, 2 to 4, and this 4 to 1. So in table 4 we get this one cycle and this other cycle 3 5 3, 3 to 5 and 5 to 3. Do not satisfy the additional constraint. In table 5 we also get two separate cycles, 1 to 4, 4 to 2, 2 to 1, 1 to 4, 4 to 2, and 2 to 1. And other cycle 3 to 5, 5 to 3, 3 to 5, and 5 to 3. So these two tables do not satisfy the additional constraint of TSP. So these are not the solution of TSP. So we shall try to assign next list value 1 other than 0 as shown in table 5. And this the assignment is 1 to 3, 3 to 5, 5 to 2, 2 to 4, 2 to 1, and this satisfy the TSP. Hence the minimum cost is 27 units. Question C. If xy be a real valued function, x and y defined x belongs to a, y belongs to b, a, b, two subsets of the real numbers, and if both max min fxy and min max fxy exist, then prove that max min fxy less than equal to min max fxy. Now, if xy less than equal to max fxy, x belongs to a, and mean fxy less than equal to y belongs to b less than equal to fxy. Let exist x0 belongs to the set A and y0 belongs to the set B, such that if x0y equal to max of fxy, x belongs to A, and if xy0 is the minimum y belongs to B fxy. Then we have if xy0 less than equal to fxy less than equal to fx0y for all x belongs to A and for all y belongs to B. This implies if xy0 less than equal to minimum of y belongs to B if x0y for all x belongs to A. Therefore, maximum fxy0 less than equal to minimum fx0y. Hence, maximum minimum max min fxy less than equal to min max fxy. Actually, this is the example of this. This is the curved surface. This z equal to x square minus y square hyperbolic paraboloid, and this is the saddle point of this. This is the maximin. This is the maximin, minimum value. This is the value, this minimum value. This is the mean xy. This function is xy, corresponding y tends to b. And this there is maximum. This is the maximum of this mean max min. For this is the minimum value, this minimum value, and this line, this curved surface, this minimum value, this curved surface, this is the minimum value. So all this minimum value is the maximum is this point, and this max of fxy. So this point, this is the maximum of this curved line, and this is the maximum of this curved line, and this is the maximum of this curved line, and this is the maximum of this curved line. So the minimum value of this maximum value, this point. Question 5D. In a rectangular game, payoff matrix is given by this. Give reason whether the players will use pure or mixed strategies. Also find the value of the game. Here, new bar is the maximum value, that is 0. This is the row minimum, this is the column maximum. So new upper bar is the minimax value, that is equal to 3. Minimum of the column maximum. So new lower bar not equal to new upper bar, hence the game has no saddle point. The players will apply mixed strategies. So we shall solve it by algebraic method. let P1, P2, P3 be the probabilities for using A1, A2, A3 strategies, and Q1, Q2, Q3 be the same for using B1, B2, B3 respectively for the player B. And thus we get P1 plus P2 plus P3 equal to 1, 3P1 plus 4P2 plus minus P3 equal to new, and 2P1 0P2 3P3 equal to new, and 5 minus 5P1 minus 1P1 5P2 minus 2P3 equal to new. And for Q1 Q2 plus Q3 equal to 1, and for Q1 this 3Q1 2Q2 minus Q3 equal to new, and new is the value of the game. And from after simplification we get this q1 is the value of this q2 q3, and new is this, and p1 is 0, and so on this. So optimal strategies for the players A and B respectively: A 0 half half, and B is 2 by 17 23 by 34 7 by 34, and the value of the game is 3 by 2. Next question: use dominance to reduce the payoff matrix and then solve the game. This here the dominance apply here. Dominance elements of third row are all less than those of second row, that is R3 less than R2. Hence our third row is dominated by second row, hence we delete the third row, and the reduced payoff matrix is this. And all elements in the second row and fourth row are greater than the corresponding elements of the third column. Second and fourth column. Second column is this, fourth column is this, are greater than the corresponding elements of the third column, is 1 and 4. So C3 is less than C2, and C3 is less than C4. So third column is dominated by second and fourth column. So we discard second and fourth column. So the reduced payoff matrix is this. The element of second row are greater than those of the first row, that is R1 less than R2. R1 is less than R2. Obviously, so we discard R1 and reduce the payoff matrix will be this. Again, B will select the strategies in which A's gain will be minimum. So we discard this. So this is the 4 is the A 2 3 is the strategies, and the value of the game is 4. Question 5. Solve the following game graphically. Let the player B play with probability Q and Q dash, with the Q plus Q dash equal to 1, and B's expected payoffs against A's pure moves. This L1Q is this 2 minus Q, 2 minus Q, 2 minus Q, that is Q plus 2 into this for Q, and this 2 into 1 minus Q. So this is the L1Q, say, for this A1 move. For A2 move, this 5 into Q and 4 into 1 minus Q. So with this the is purely based expected payoff. Consider two vertical lines Q equal to 0 and Q equal to 1 with unit distance apart. We draw expected payoff lines L, J, Q, that is J equal to 1, 2, 3, 4, 5 in the following. And this, the player B wishes to minimize his maximum expected payoff. So we consider the lowest point of the intersection Q of the upper envelope. This point is the intersection, this is the point Q, intersection of A2 and A3. This is the, and so the reduced payoff matrix is this corresponding this 5 4 and 5 4, and this the minus 7 and 9. And solving we get this Q equal to 5 by 17 and Q dash equal to this 12 by 17. The value of the game is this, L2 is this, and 4 plus 4 5 by 17 73 by 17. The optimal strategies for A will be 0 P P dash 0 0 with P plus P dash equal to 1. So we get the optimal strategies for A is this and B is this, and value of the game is new equal to 73 by 17. Thank you for watching this video.